Okay, so the thing is, on Wednesday last week, we covered a fair amount of essentially backprop, and we looked a little bit at mini batches and just, taking updates through the parameters of a deep network. So for all practical purposes, our deep network is one beast with many parameters and knobs on, and we essentially want to update the value of those parameters in such a way as to improve some form of a score, right? So that was where we left off last week. Now, this is kind of hard. It's kind of hard if you have a lot of parameters. And so the idea is maybe you can use some prior knowledge to incorporate into your model such that you can then learn the parameters a little bit faster. And so I'm going to start by talking a little bit about invariances. And this is probably a slightly different treatment from what you see in the books. It's basically a little bit more group theory heavy. So if you've probably seen that game or some version of that. It's called Where's Wally? So you have this huge picture. I actually didn't bother trying to find Wally, but Wally must be somewhere on that picture. But he could be here, he could be there, he could be there, he could be anywhere, right? So the problem is, what you could now do is you could basically learn a Wally detector, right? So this is, it would be a very primitive project, but you could do a computer vision project about a Wally detector. Now, the problem is if I need to learn the Walliness of this spot and then the Walliness of this spot and so on separately, then I would need a lot of training data, because I would need basically to get a Walliness example for anywhere in that image. So that would be a lot of images. But we all know that once we've seen Wally once, we know what Wally looks like. I think he usually wears a red hat. And you can find him somewhere in that picture. So in other words, we have a certain amount of invariance and prior knowledge about how things work. So we know that if we want to detect objects in an image, the position of the object isn't quite so important. Yes, it is important because cars don't fly and nor do pigs, but birds do. But other than that, effectively, even if you saw a flying car or a flying pig, you'd still recognize it as such because we know what a pig looks like, right? So in other words, the parameters for the detector should be location independent. So that's the key point. So therefore, we can actually tie the parameters for the object detector between different locations. And I'll get a little bit into what that means on the next few slides. So let me first show you the solution of this idea. And this is what was called Lunette, because Yann Lequin came up with Lunette. And that was essentially state-of-the-art 1990s. So what it does is basically for optical character recognition, it takes some input, it convolves this in many ways, and then it subsamples and it convolves it again, it subsamples again, and then you have a couple of fully connected layers, and that in the end will give you a means of inferring, what that character would be. So here's how you can really get to that. Well, the first thing is that the images have some degree of translation invariance. So this is exactly the Wally detector. Wally could be anywhere in the image, and it still would be Wally. The other thing is that low level, mostly we have edge detectors and other very primitive operations that are very primitive and that are local. And enough cats have been sliced open and so on and detected where you basically feed them stimuli and then you can test the receptive field. So Hoover and Wiesel, for instance, did that. Where you can basically find out that a lot of the low-level vision features look essentially like edge detectors, right? So these are basically edge detectors or pattern detectors of some form, or then colors and all of that, right? So can we actually engineer a neural network which takes advantage of this knowledge that we have from slicing up enough animals and also from playing various Wall-E to basically determine what our parameters look like? Well, actually we can. So the first thing that we can do is we can use what's called feature locality. So if you just wanted to design a fully connected network, then what I would do is I would take the entire image and take it as one big fat vector, multiply each of those coefficients with some weight wij ab, and I've just used those double indices because images have an x and y coordinate, but you could basically just flatten it out. And I would have those coefficients, and I would basically apply this to xi plus a, j plus b. So I would do that, right? But since I only care about a local region, because Wall-E is usually small and not gigantic, so therefore I only really need the weights locally, so I get this. But what I also have is I have a translation invariance. In other words, whether I have just those coefficients a, b, or whether I have location-specific coefficients, well, actually I can drop this index, right? So this would be just a matrix vector multiply. Here it's, again, that same operation, but just that I'm using the same operations regardless of the location. And that's nothing else than a convolution. It's basically some local weighted averaging of a patch. So convolutional neural networks really exploit two properties. Locality, so that means the size of the operations that I apply per patch is kind of limited. And translation invariance, which means the parameters that I'm applying are the same regardless of where I am in the image. Okay. Yes?
Could you please once again say why can you drop the ij index?
Mm-hmm. So that is basically the translation invariance. So if I wanted to make the most general assumption, then for every location ij, right, I would have a different set of parameters, right, in order to get some linear combination as a result, right? Because I have a vector in, I want to get some parameters out, maybe of the same dimensionality, and so therefore I would have to, have a different set of weights depending on which neighborhood of the image I'm looking at, right? So that's why I first have this additional index ij on the weights. It would also mean that rather than just a 5x5 convolution mask, I would have to store a 5x5 by number of pixels in the image mask, which would be way bigger. So that's how you can see why translation invariance can drastically reduce the number of parameters. Very nice recent example is the Inception Architecture versus actually those convolutional layers with densely connected. And basically, so there are links in the slides, don't worry. So the Inception Architecture essentially has less than 1/10 the number of parameters and actually works slightly better. So, which is kind of nice. Yes?
But this assumes that we know the scale of the object.
Exactly. So I'll get to that scale part a little bit later. You're absolutely right. It assumes the knowledge of the scale. Now, you can actually engineer around that by, for instance, having a filter that has its parameters tied across scales, where you would say, well, depending on, regardless of the scale, I always want to have the same set of filter coefficients. So there's a paper that came out last year. I forgot the names of the authors. I think they came out of Hong Kong University. Essentially, a lot of authors with 3-letter names. Sorry, I'm bad at remembering some of those. And they did a very nice job at essentially modeling this. But there are other tricks how you can get to that as well. Yes?
And when you're training this, when you backprop, do you average over the errors for all the different
Exactly.
combinations?
So, well, what happens here is that now your parameters are tied between that. So that means now for the gradient, you end up adding up all the partial gradients, right? It's just like, well, any other function parameterization. If some parameter occurs in a few places, you need to apply it in a few times. So that's one of the immediate ways of seeing that you now get the aggregate effect across the entire image as opposed to just a local one. It's actually a very nice way of seeing it. I have a question for you guys. Can somebody else tell me where this thing might break? We already had scale. Which other things could break it? Or basically, where else is that assumption wrong? Rotation.
And scale.
Okay. We already had scale, but rotation is good. What else?
How do we have scale?
Well, what happens is, once you're at the boundary of an image, right, you're starting to lose pixels. And this is something that in a lot of computer vision applications, people just sweep under the rug and they just ignore a couple of pixels on the outside, which is fine for images, and it's really not okay for text. Because throwing away the first few and last few words of a string will completely garble text, and I'll show you how to work around that.
But still, a model that's trained, let's say, on faces that are really small,
Mm-hmm.
would that same model work on faces that are bigger?
Yes and no. Okay, it will fail spectacularly if you don't exploit that prior knowledge, right? So, because the poor network doesn't, or the poor model doesn't know that there are larger faces out there. Maybe you are trying to identify tiny faces, right? So maybe that's exactly the goal of the entire project. Now, if you know that you're interested in faces as opposed to tiny faces, you would have to either engineer this into the function class by enforcing scale invariance, or you may have to generate artificial instances of larger faces to actually detect that. So for instance, if I take a picture of you guys and there's one tiny excised face somewhere in the middle, I probably wouldn't want it to recognize that as a face, or at least this, I think everybody would agree, would be quite an anomaly. So if I had a tiny head on my shoulders, you would think, gosh, what a weird professor, right? So that is exactly an example where, well, we have some scale invariance, so maybe my head is a little bit smaller than everybody else's, but if it was really tiny, then probably you would be completely creeped out, right? So, and we'll get to invariances in a moment. So, how would you actually implement this? So, the first thing that you probably do is when you read convolutions, you think about your EE lecture about signals and systems or something like that, and you would think, okay, well, we can use Fourier transforms, multiply in Fourier space, and then we have something log linear. Alas, that's too slow. Actually, brute force multiplication is really what wins the day on basically modern GPUs, because they are just amazingly good with floating point performance. Okay, so that's basically what it is. One thing that I should mention, and this is something that's a bit more of a recent development. So the problem is if you keep on doing this, right, you convolve, and you get actually, you start with one input image. And if I have maybe 100 different convolution masks, I already get 100 images here. And then maybe I do some other things with it, and maybe a lot more convolutions, and then even more here. Then what's going to happen? Can somebody tell me what the really horrible thing might be that happens if I keep on doing this? I have, well, what happens is I get way too many parameters. So they end up eating up all the main memory. Mind you, if you're implementing deep networks on a GPU, it's not the parameters that kill you, but it's all the intermediate data that you need for the forward and back prop that will basically make you run out of memory. It's that, or rather than the mini batch size. So we had that very question in one of our mailing lists just last week. where somebody was very surprised, well, why doesn't it fit on a small GPU? Well, it's all the convolutions. Now, one way of fixing this is basically by convolving and then subsampling. Right? So you basically just downraise the image. You keep on doing that. And then, of course, each time you downraise by a factor of 2, you need a quarter of the bits. So this is easy. The problem is this isn't very translation invariant. So instead what people do nowadays is what's called max pooling. And max pooling just means, well, you take the largest over all the coefficients. So this is the subsampling operation, right? And this is the max operation. Right? So it's fairly straightforward. By the way, you could actually interpolate between those two. Can somebody tell me how to do that? Is there a function which, in one limit or another, results in the average, and in the other limit results in the max?
Softmax.
Softmax, exactly. So let me quickly write that out. If I have, let's say, A plus B, then, and I have max of A plus B, then what I can do is I can look at something like log of e to the A plus e to the B. Okay, this is the softmax. Okay, so can somebody tell me what could go wrong if I was to use this in anger? What could happen if I implement it on a computer?
Numeric underflow.
I could get underflow. That basically means it gets rounded to 0. What's the other thing that could happen? What's the other end? There's underflow. There's overflow, right? And basically what happens is, if you have floating point numbers, let's say this is my floating point number, then there is usually one bit allocated for the sign. So this is plus minus 1, so to say. And then here I have the mantissa, and here I have the exponent. Okay. The mantissa is about 2/3 of usually the bits that you get, and the exponent is about 1/3. The specific details depend on exactly the hardware and all that, but you can look that up on Wikipedia exactly how many bits you have. Now what happens is, if you're exponentiating things, you're pushing everything from the mantissa into the exponent, and you've drastically reduced your bit resolution, right? So for instance, on a 32-bit integer, you might have 10 bits here and maybe 21 bit there. And so now all of a sudden you're short of bit, you're pushing everything over there, you're doing operations, you're pulling them back, and you run out of space. So how to fix that? Does somebody have an idea?
Shift it minus max.
Exactly. So let's assume, I'm just being lazy here. No, actually let's not be, well, yes. Let's assume without loss of generality that A is greater than B. Actually greater or equal than B. Then what I can do is I can write this as A plus the log of 1 plus e to the B minus A. Okay. Now if I do this, it becomes numerically a lot more stable. Right? Because B minus A is now less than 0. So I get something that's 1 plus a little bit extra. Right? So we know that this is always less equal than 2. Right? This is now numerically stable. The only thing that could happen is if A is really way bigger than B, e to the something fairly negative becomes 0, and then I basically get A out of it. Right? But now I've essentially fixed all the numerical instabilities. So this is a fairly useful trick that you should probably look at. So, simple example where this is used is this operation, right? That's the absolute value of x. Well, that's nothing else than the max between x and minus x, and which is log of e to the x plus e to the minus x, right? This is a good approximation. Now that also tells you that if you have that type of operation, which is just this, okay, I'm drawing it horribly here, but I guess you can try that out yourself. First of all, this gives you, an upper bound on that. Secondly, it's differentiable. Third, if you want to implement that and you get large x, then a much easier way of implementing this is to take x plus log of, somebody tell me what I should write here. 1 plus, okay, how does it continue? E to the minus absolute value of x. Right? That's a stable way of implementing it. Okay, good. So, short detour on that, but you need that in some of those cases. You very much need that also in graphical models. When you're dealing with probabilities, you're multiplying them. Numerical over and underflow are a real pain, and if you are not careful, you pay dearly for it. Okay. So, okay. Now, let's look a little bit at structures. So, at some point, people started asking questions, how many convolutional layers do I really need? On top of that, you could even, ask the question, how wide should they be? So, for instance, if I have a 5 by 5 convolution, right? 5 pixels by 5 pixels. Then I can get it this way. I could also have a 3 by 3 convolution, and then another, 3 by 3 convolution on top of that, right? And those two 3 by 3 convolutions combined would essentially cover the same area as a 5 by 5, right? Now, which one is better? Well, a priori we don't know, so that's why they actually did a nice experiment there. And you basically see a large set of different combinations that people essentially tried, and they looked at, generalization performance. And the interesting story there is essentially deep and narrow is better than wide and shallow. Which, okay, begs the question, why might that be the case? Anybody have an idea?
Because you have more non-linear layers.
Perfect. That's exactly what it is. So you have an extra chance of having a nonlinearity somewhere in between. And that's basically why those extra nonlinearities give you more expressive power. And that's basically why it works better. You get a lot more expressive power without too many additional parameters. Right. Okay, so then, of course, you can ask the question, well, is it really the case that there's maybe one best parameterization, is 1 by 1, 3 by 3, 5 by 5, or whatever, really the optimal thing to do? Well, turns out there isn't really. So instead of deciding upon one specific solution, you can go and pick several of them. And you just paste them together afterwards into a large vector, and then you apply things again. Or you go completely crazy, and you take 1 by 1 and 3 by 3, and 1 by 1 just means apply nonlinearity. And you basically apply all those transformations at the same time, and then you take the next step. So this is essentially a strategy for covering a large range of different structures. And this is then what the Google Brain team called the Inception Architecture, as in we have to go deeper. Yeah. Okay. What you get is something like this. Right? This is the GoogleNet architecture, and it's basically too ginormous to really plot it in any other way and still see it. So really have a look at their paper. That's directly where this is grabbed from. A couple of interesting things there. So first of all, you see those repeated structures. What you also see is this yellow box and then this black box, black empty box occurring in a few places. And what this really is the objective. Namely, in this case, for instance, the category, whether it's a cat, a dog, or a car, right? And it occurs in more than one place. What they do is they essentially add the objective in several points to ensure that whatever features you are getting are really well tuned for prediction accuracy. Yep?
Is this handcrafted?
Yes, of course. Very much so. But at least it's only handcrafted in terms of those repetitive structures, right? But if you want to build something decent, then right now they essentially perform optimization over engineers, right? On the other hand, one engineer to try things out for a couple of months to solve a specific important problem is probably an okay price to pay. You can go much fancier than that. The good news is you can actually make your life easier. So this is something that Muli's been working on lately. This is, straight up example code from that. So this is basically, let's say I want to do a, Inception-like structure, and I only have 1x1 and 3x3 convolutions. Then what I do is I go and define those convolutions. This is runnable Python code, so the entire example is less than 300 lines of code with everything included. You concatenate things together, and voila, you have a runnable deep learning system for recognizing objects. So I'd strongly recommend that you have a look at that. So the URL to remember is github.com/dmlc, and then you'll find MXNet. So there's a lot of stuff there. And this is essentially the latest system. It will run on CPUs and GPUs quite nicely. And I would suspect that it's very competitive with pretty much anything else out there. And a lot easier to use. Okay. So if you want to do deep learning, you should check this out as your library of choice. Also because, we have some of the developers here, so this will help you if you get stuck, and you should give feedback to them. Okay. Any questions so far? Okay. So now let's get to the issues of, why convolutions aren't the answer, right? So, because, I like cats, so let's do some experiments with cats. And there's a couple of things that you can't really handle very nicely with just convolutions. Yes. So shifts work really nicely. Scaling fails. But you may not necessarily want to scale completely, because if this was the size of the human and that's the cat, then it's maybe, a Tyrannosaurus cat or something. Rotation, to some extent it works. If you turn a cat upside down, then it probably looks like a dead cat. Color space, it definitely matters. First of all, cats come in all sorts of colors. Secondly, camera calibration can be horribly wrong. So we know that this is an important invariance. So we want to be able to actually incorporate all of that efficiently. So in the interest of time, I'm going to skip entirely over text parts. Please read that up. There's actually a pretty cool paper. So Kaltenbrenner, Grefstätte, and Blonsum. You should really read that paper if you want to do anything with invariances and text. What I'm going to, and this is all on the slide, so don't worry. What I'm going to do is I'll talk a little bit about approximate symmetries. So approximate symmetries are exactly what you want to do if you want to deal with some changes, some degree of prior knowledge. So first of all, the top line already tells you why full symmetries may be a stupid idea, right? So let's say I have a little bit of rotation invariance. So in other words, if I stand like so, it's probably still me, and at some point, well, I fall over. But if you take a 6 and you keep on rotating it, and at some point you get a 9, then, well, clearly somewhere the symmetry went wrong. So we could probably argue that the first 2, maybe 3 digits would still be a 6. Then something is really horribly wrong, and then the last 3 are probably 9s. Right? So that means we can apply some of those symmetries approximately locally, but not really globally. And that may actually also depend on what object I'm looking at. So for instance, if I have daisies, well, they stay daisies no matter how you rotate them. Cats don't like to be put upside down. With text, you have some approximate symmetries in the sense that you can insert or remove a few words, and then it's still okay. With audio, well, background noise doesn't change necessarily what I'm going to say. It might just make it a lot less intelligible. And if I was to inhale helium and sound like Mickey Mouse, it would probably also, okay, it would sound weird, but it would still be machine learning. So, with that out of the way, let's look a little bit at what you can do from group theory. So, who's done group theory before? Okay, so those of you who haven't, don't worry about it. It's basically, think of it as a set of operations or transforms that you can, in this case, apply to the data. One way how people get, averages in group theory is, for instance, you can go and just, sum over all the transformations that you could do. And then, of course, you get an invariant object. Or you could take the maximum over this. And, of course, the little puzzle is, how can I go from the maximum to the average, right? And I guess everybody knows how to do that, because the answer is over here, softmax. So this way you can interpolate. But basically, if you do that, then you get invariances. Now let's see what that actually means in terms of machine learning. I could, for instance, take a loss function. So let's say misclassification or whatever, and I keep on rotating my images a little bit. And what I want to do is I want to make sure that I get things correctly for the original data, but then if I get things wrong for approximations, then maybe that's not too bad, right? So what I basically have is I have, this data, which is maybe slightly being corrupted or transformed, but if I incur a high loss there, basically depending on how strong this transformation G is, I will weigh it differently. You could also multiply those two terms if you wanted, right? So that would basically just mean that I only care about invariances within a certain neighborhood region. Likewise, you could do that with the maximum. Again, whether you take differences or whether you multiply is pretty much a matter of taste. Well, why would you care about this? Because, sorry.
Does that delta play the role of like a regularizer?
So this basically is, well, in a way, it's the opposite of a penalty, right? It's basically how little you care about the about making a mistake for a very extreme transformation. So, in other words, if G is a rotation by 90 degrees, then probably delta of G, if I make it multiplicative, should be 0, because then I basically shouldn't care anymore. Or if it's additive, then this should be about, as large as the loss itself. So, or for instance, if I have, a image corrupting transformation where I reduce the bit resolution, then as I reduce the bit resolution, it'll get harder to recognize me. Until at some point, well, you just can't find out that, well, there's probably a human there. And in which case, it's impossible to find out that this is Alex as opposed to just a human. And you shouldn't really have to pay any loss for that. But this way, you can virtually augment your data set by basically creating a lot of those instances. This is actually a really old idea. So the virtual support vectors from around 97 or 96 that Bernard Shelkoff proposed, for instance, do this. Tangent distance does something like that. This has recently been picked up again. So Yann LeCun, for instance, used it as background clutter for an object recognizer. So this was one of the, maybe about a decade ago, the early general object recognizers. They would take the objects and just, put them in front of, random clutter. And the idea would be if your object detector works well, it should be able to handle all this random clutter. And through that, you make it more robust. For instance, the deep speech, or whatever it's called, system of Baidu for a speech recognizer used that quite cleverly by just generating a lot of different background noise with a speech to be recognized. And actually for speech, this is a very reasonable model. I mean, you have reverb, you have background noise, other things. And maybe people's speech doesn't change that much independent of that. And since it's pretty much additive, you can optimize over it. Or then for images, you can subsample, you can take patches of the image, you can rotate it, you can distort it, you can change the color space. And that's then a function of how much GPU resources you have available. Yes?
So you don't actually analytically represent these transformations and then carry the background.
Exactly. So that's actually the key observation. Rather than using group theory invariants that are exact, in many cases, first of all, you don't have an exact invariance anyway, because an upside-down cat is not a good cat. But a slight rotation is probably okay. So you keep the spirit of what you have in group theory, basically those local generators, those local transforms that should keep things more or less invariant. But you don't necessarily enforce it entirely. The good thing is also that now you can apply this to approximate invariance that you can only specify algorithmically. So for instance, one of the invariants might be do a simple transformation in Photoshop, right? And we all know that a simple transformation in Photoshop probably will leave things sort of kind of recognizable. So you can change slant, you can change line thickness. There's a lot of things that you could change for instance, optical character recognition. Maybe fewer when you do face recognition, because people usually don't distort their faces, so the geometry is fairly fixed. And that's actually what lets us recognize people fairly accurately. But they can frown or change their hairstyle or wear glasses or grow a beard, at least some people. And so by using that, you can get a little bit more invariances and then do good recognition. Yes?
Why over there you have two ways of rating? You have delta and you have p.
Yes. Okay, so that's the other thing that you really want to do. You basically want to have some, and actually the bracket should probably go around this here, really. So essentially, this may be a way of just weighing how important or likely some transforms are. Right? So for instance, with rotations, I might limit myself to rotations of at most 5 degrees. Or maybe I mostly have the rotations up to 5 degrees, but occasionally I'll throw in a few up to 10 degrees. Right? So that may be a way of modeling the degree to which things are invariant. This is a great way of boosting performance essentially for free. But you need to know your problem. Okay. Any more questions on that? Okay, good, then let's move on. The last thing is that deep learning by now is essentially a moniker for pretty much everything that's nonlinear and non-convex. So the obvious thing is that what you really want to do is whole system training. So if you have a large system where you have separate operations, then training the whole system will considerably improve performance. So case in point was actually a system that was built in the 90s at AT&T, And this was for essentially check reading. Like when you write a check and you send it to the bank and it scans in, all that. So they started, so this was in Jan de Kaan's team actually. They started by basically handing out individual portions of the project to individual engineers. They would build stuff, they put it together, and it was a spectacular disaster. It didn't work. The reason why it didn't work is because each system made some errors, and all the errors compounded each other, and so things went badly wrong. How to fix that? Well, what you can do is you can basically go and then optimize over the whole system. You propagate gradients through everything, and that will considerably improve accuracy. So that's effectively how you can actually do much, much better whole systems training. And there's a paper that's very important, but, well, the writing is a little bit by pasting chapters together, so some chapters are quite different from others, but it's an important paper to read. I think it's way underrepresented, undercited. Let me give you another example of where something like that didn't happen. So some company used to have a search engine where you would have different stages of rankers. You might have a first stage ranker which just finds out whether a document is on the topic at all, a second stage ranker which would then decide whether it was actually relevant really for the query with a more expensive operation, and then maybe a representation layer which threw stuff on the screen. And there were 3 teams working on those 3 components. And every month or so they would improve their components, and then they would run things again. And then occasionally and each of their metrics individually would work, and they would improve their metrics. Then they would put things together, and stuff would blow up occasionally every couple of months. So what happened is basically that they did not do whole systems training, because improving a subsequent processor or ranker might only help if the previous one didn't also change and now all of a sudden started sending different errors through. And so basically they did backprop through email and phone calls. And that search engine doesn't exist any longer. Talk to me more if you want to know about details, but not on the record. Okay, good. Any questions about this? Good. So let's go very quickly through different objectives. We're not going to finish all of deep learning. Barnabas will cover a little bit of it next Monday, and the rest is really for you to read up directly, because there's a lot of progress that's been made in the past few years. You're not going to be able to get through all of that in about 3 lectures. So remember regression classification. We had some scores which compared, a label Y with some output F. And then, for multiclass classification, what you could do is you could, for instance, do something like predicting the next word. This is actually quite a popular thing in, for instance, those word-to-vec type of embeddings. And so you could then, read in this text and then find out whether, oh wow, I found what the likely next word would be. And my guess is dinosaurs would be on the lower end and theorems a little bit higher here in the machine learning department. That's a simple objective. Let's think of something a little bit more interesting. So we'll cover principal component analysis later on again, but let's think of something very, very simple. Let's say I take my data and I project it down to a lower dimensional space, and then I try to reconstruct it by having, some matrix V1 to get X3 out of it. And so what I might want to do is I might want to minimize the discrepancy between X and this operation. Now I'm going to spare you the mathematical details here to show that, the optimal thing that you could do is principal component analysis, where you basically project onto the leading singular vectors, and then you reconstruct from that, right? So this is kind of standard, and Barnabas is probably going to cover that in a fair amount of extra detail, just principal component analysis later. But the thing is, why stop at being linear and why stop at 2 layers? So the first question actually that I have for you is, if I didn't use nonlinearity, what would happen? So, by the way, so this is compress, compress, compress. Here's the code, and then you decompress, decompress, decompress. If I didn't have nonlinearities but had everything linear, what would happen?
Just reducing the rank of the...
Exactly. So it would. There's no benefit in having multiple layers. It's really just the compression from original to, the smallest dimensionality that matters then. So if I go from 1,000 to 5 dimensions, anything that I do here in the intermediate steps is completely irrelevant. It's just that. Because the composition of 2 linear functions is again a linear function. That's why. So the only way to work around this is by adding a nonlinearity per layer. So there's, for instance, one guy who's done really great work on this, who will be joining CMU's faculty next January, Ruslan Solokuditnov. He's basically built deep Boltzmann machines, restricted Boltzmann machines, so you should probably take his class if you're very interested in this. I don't know whether he'll be teaching next spring already, but basically he's done a lot on that type of representation. But the point here is, what we can do is we can apply a nonlinearity at each step and then decode things again. And the idea is that by allowing for this nonlinearity, I can encode more information than what I could otherwise. One of the nice things is that, well, basically this code C has all the information, or more or less all the information about the data. So if I perfectly manage to reconstruct everything, then if I knew C, I didn't actually need to store x1 to get x1 back, right? It's just like if I gzip my file, then this is, a compressed representation of the file. So I don't need the original file, I can throw it away, and then I decompress and I get the original file back. So in that sense, the gzip of my text is a sufficient statistic of my text, because I don't need the text anymore. And the idea is essentially that this autoencoder will approximately keep this. Why is it good? Because this way, for instance, if I have, let's say, a picture of a cat, then the hope is that by running an autoencoder on cats, dogs, and whatever, I will manage to essentially learn what the essence of a cat or a dog or a dinosaur or something else is, right? It's probably not going to give me exactly the same cat back, but it's going to give me something back that looks fairly cattish, right? Okay, so then the question is, okay, sorry.
I don't quite understand the approximation x and cx. And then...
Okay, so C is the code of x, right? So P of y given x, if I want to predict something like whether it's a cat or dog, well, if I condition on x and C of x, nothing changes, because C of x is just a function of x, so I haven't really added any extra information, right? Now the thing is, if I manage to reconstruct, so actually what I would have had to write here is really x of C of x and C of x, right? So if I replace x by x of C, and I get almost the same thing back, then that means that probably, P of y given x of C and C should be very close to this. And of course, if that's the case, then I can drop this entirely because it's just a function of C. And so what I've just done is I've shown in a very hand-wavy way, and you can probably formalize that depending on the function class, that P of y given x is approximately P of y given C. Right? So, and this relies very much on, x of C being close to x. Okay. So, and of course, this also means I can then, just inject some garbage into the code layer and see what comes out of it. And people have done that lately. For instance, all those deep network streams on fantasies, on images, pretty much work this way. So I'm fairly sure you've seen those images. If you haven't, search for it. I mean, there are websites that basically will generate that for free now. Any other questions? Okay. So the obvious question that should arise is, okay, so I could do that, for instance, with text, right? I take text, I encode it in some way, either by this autoencoder or by some other structure, and I emit the text after that again. Well, what if I wanted to translate English into Klingon, right? So what I could do is I could encode English and then just attach to that a Klingon decoder, right? Or a French decoder or an Italian decoder. And so this way I get very quickly a natural language translation system simply by having one encoder and one decoder, and I just convert formats into each other. And this works if the intermediate representation is sufficiently general. Right? Yes?
How would that work for text? What would be the base representation?
Well, so what you could do is you could, for instance, first train a really good representation for English that emits English from English. You could do that also for French, and then you could learn a mapping between the two. So this is, or if you already have a lot of matched pairs, you'd basically optimize that just like an autoencoder, but now directly. So for instance, what you can do is you can start with natural language queries on one end and emit SQL queries on the other end. So that's what basically Kochbrenner and De Freitas and others did, and it works very nicely for natural language queries and exactly SQL. You could also do that with movies and actions, but basically you have, one language, the embedding, another language, the embedding, and then you just want to match things up. Okay. So I know this is at the moment going a little bit fast. The main reason being that I want to cover at least some of the material before time runs out. You'll probably want to read those papers if you want to get more of an idea. Okay. Any questions so far? Okay. So there's one neat thing that I snuck in here that's actually quite important to making these things work. Because if you think about it, what you're doing is you're mapping things into some representation. And you want to make sure that, yes, the correct thing is properly decoded. But you also want to make sure that it's sufficiently far away from the incorrect thing. So for instance, if you say, I want to drink coffee, and then, well, maybe I want to drink tea should be closer than I want to write the paper, right? Maybe not for machine learners. No, I'm just looking for something to wipe the whiteboard.
It's over to chair.
Oh, yeah, thanks. So what you want is basically the equivalent of a large margin setting. So we talked about large margin a little bit before, right? Where we basically said we're interested in making sure that f of x and the correct label is greater or equal than f of x and y wrong plus some delta of y true and y wrong, right? This was the large margin setting that we had. So I just showed you a convex version of this inequality with slack variables, but that's basically what we required. Right? So therefore, if the mistake is very benign, then I don't impose a very large discrepancy in the scores. But if it's very large, then okay, then I want to have a large discrepancy here. Okay. So if we were to plot this, here is, class 1, maybe class 2 and class 3. So here's basically f of x and y. Then what I want is that, f of class 2 can be fairly close to f of class 1 if misclassifying things between 1 and 2 isn't too bad. But so let's say here I have diamond. Here I have maybe ruby. Not sure why anybody would mistake a diamond for a ruby, but you definitely you don't want to mistake it for coal. Right. Now, we want to have something very similar here. What we want is basically that the distance between A and B is much closer. So if A and B are, supposed to be matched into each other or, decoded from each other, that this is much smaller than the distance between A and some detractor N. And how do I make it smaller? By essentially pulling this over. Delta of A and N. So here the distance is small when things are correct. There the score is large when things are correct. So that's why you get the delta on the other side. And then of course, since this cannot always be satisfied, I add a slack variable and I get this. Right? Okay. Is everybody cool with the transformation from this line into this line? Few skeptical faces. Let's say, plus some variable psi. And so what I get is that psi is greater or equal than delta between A and N plus d of A and B minus d of A and N. And we also know that psi has to be greater or equal than 0. Okay, and then we're done, right? Because then all I do is I just combine this into the max of those two terms. Done. And so now I can go and minimize psi. This is essentially these contrastive maximum margin losses that you can use. Okay. Obviously, if you want to implement that, you probably want to read this paper, but that's one of the neat ideas in there. The other one is just to then, look at a large class of such encoders and decoders. So for instance, if you want to annotate images with text, you could have an image encoder and a text decoder, and you map it across. Or if you want to generate images from text, you encode the text, and then you decode the images, or you find the closest image in whatever representation to the encoding of the text. Okay. So let's sum it up. What you really need as key components is, well, you want to have some way of optimizing over the gradients. Backprop, aka the chain rule, is a really good way of doing this. The next thing is you need layers, which basically capture, the data, do something interesting with it, and then they emit something interesting. And if you have certain structures that work really well, then you basically want effectively to define macros. So this is starting to look very much like what you would do in chip design, where you don't necessarily, if you design a processor, design every transistor, every gate individually, but you have macros of, well, okay, these are registers, these are memory cells, these are processing elements, and then you just replicate this. And that's what's starting to happen a lot more in deep learning as well. You want to have certain types of nonlinearities that are easy to deal with, and basically people try out a lot of stuff. And then you want to have a loss function, which basically needs to specify what your goal is. Sometimes you get nice intermediate results. So for instance, when people try to do object recognition, as in ImageNet and other things, they will have a number of convolution layers, and then in the end they have some dense layer, and then they get a prediction, right? And sure, this is useful for that, but you can also use the attributes before the last layer as really good feature maps of your images. So in other words, you can train on one data set and then use those features for other things. And that's kind of neat. But that's more a lucky coincidence than necessarily that, something you did by design. Even though a lot of people will claim otherwise. Questions? Everything clear? Yes?
Are there cases like where whole system training is a bad idea, where you can actually get worse performance?
Yes, that can happen. So here's what can happen. What can happen is, first of all, that you will end up getting into a really poor local minimum. This is probably the number one biggest problem, right? In that case, well, you basically screwed up your training. Here's another thing. So let's assume, well, we're back in our check reading system, and we have a lot of data for the image segmenter, and we have a lot of data about what the actual text is that people will write, so basically the actual language model. But I have very little data for whole system coordination. In that case, I can't really immediately naively use this data on those subsets very well, because I'm just training the whole system. And so in other words, if I don't have nice end-to-end data but only modular data, then whole systems training may actually work worse. But there are nice ways of working around that. For instance, you could say you want to have a system that works well as a whole system, but also that decodes well as any of those intermediate pieces, and then you immediately made your life a little bit less painful. So whole systems training is good, but you need to try to incorporate as much invariance, as much additional data as you have. Or for instance, if you have a natural language translation system, then the thing that is really plentiful is untranslated text, right? The thing that's really expensive is the aligned text that is given in multiple languages, right? So that's why it's really expensive, for instance, to have 10, 15 different European languages, and only the European Union, the European Parliament, will actually do this. And there's something called the Europile dataset, which is basically everything European politicians say multiplied by 15 in different languages. In practice, you don't have that. So now you can, for instance, try to use additional underlined data to make sure that whatever your translation module outputs will actually sound like the target language. But that's not necessarily a great idea. Can somebody give me an example where just requiring that all, let's say, North American documents translated should sound like documents from, let's say, in Hindi? Why is this a bad idea? What could go wrong? Do you think that articles about the latest Super Bowl are really a big seller in India? Probably cricket's a lot more exciting, right? and maybe elephants, and maybe local corruption scandals rather than American corruption scandals, or Donald Trump's hairpiece is probably not so exciting. So what you have is you have different distributions, but you also have covariate shift. So not only is it a different domain, but also people talk about something else. So what you then want to do is you want to make sure that the documents that you translate, or that you automatically then translate, sound very much like the matching documents that you would find, let's say, in Hindi, as opposed to all the documents that are there in Hindi. So you basically have covariate shift in addition to the translation problem. So what that means is there's still room for lots of nice research. So what I just mentioned, this is actually something, if you want to do research on, talk to me. This could be a fun project. Secondly, well, covariate shift itself is also an important problem to worry about. I think we're pretty much out of time, so I'm not going to go into optimization very much, except that Barnabas will cover a lot of that and drop out in the beginning of the next class. That's it, since he also needs to move on. Basically, read up on some of those things. Also, just from the slides, there are plenty of pointers in the slides. Or then ask me after hours now. Or, for instance, there are entire courses on deep learning. So probably the most exciting one right now is the YouTube class of Nando de Freitas. So he has a nice YouTube channel. This is I think 15 units as opposed to 3 or maybe 20 that he taught in Oxford last semester. This is something that will contain a lot more detail and a lot more things. So it's both broader and deeper. And basically, listen to his lectures. You might enjoy them quite a lot. He's a very good lecturer. He just has a lot more time to cover this than I did right now. And okay, good luck with it. Okay. Would you mind pressing the stop button?